Move to the second speaker, who is Marco Cook from Glasgow University. So whenever you are ready, you can start.
Okay. Hi, everyone. So my name's Marco Cook. I'm a researcher at the University of Glasgow. I'm going to talk to you today about some of the work that we've been doing on digital forensics in industrial control systems. So I just mentioned to start with that this work was funded by EPSRC and DSTL, the Defence Science and Technology Laboratory, part of the Ministry of Defence. So let's see if this works. There we go. So I thought I'd just introduce the team to start with, since we're all doing this virtually. So is me there, hopefully you can see me on the camera. And we've got Professor Chris Johnson, who's the head of the lab at the University of Glasgow. And then we've got Sarah Dimmock and Ioannis Stavrou, who unfortunately we couldn't get a picture of, but those were two master's students that helped us with some of the research and experiments that we did on for this project. Okay, so what are the areas that we're, the technologies that we're looking at? So I'm sure a lot of you know or have heard of industrial control systems or PLCs before, but there's often a lot of kind of blurriness between, you know, what is operational technology, what is industrial control systems. So I included figure 1 there just to make sure that we're all on the same page with it. I see critical national infrastructure as the wider picture or sector, so such as telecommunications or electrical generation. And then within that, you'll have IT systems, which are on your corporate side, but also your operational technology. However, your operational technology also consists of IT systems, but there's a part of your operational technology which is just your industrial systems. And these are the systems that are used to control the real world physical processes to drive the operations that the business requires. And within these, we have PLCs, which are specialized computers that are specifically designed to operate in high intensity environments within industry. So a lot of them have a lot of fail safes. They have a lot of redundancy so that they can operate in safety critical environments. And I've included a couple of pictures there on the right, just if no one's ever seen one before. We've got a S7300 from Siemens there, which is more of a legacy device, and then a Rockwell Allen Bradley PLC as well, which is more recent device. I guess the question is, why is forensics important with this? Well, it's important to acknowledge that a lot of these are homogeneous in the sense that we might have two different organizations or two different sectors in C&I that potentially have different aims and objectives, but commonly we see the same systems transferring and being used into different environments, which means that the threat that might exist or be opposed to one sector is also transferable into another. And therefore, it's really important that we understand how potential incidents or existing incidents have been achieved and try and develop or better develop defensive solutions to prevent them from happening again. Okay, so what was our research problem and aims with this project? So there's been a lot of emphasis over the past couple of decades that's been placed on digital forensics for IT systems, particularly with the introduction of systematic approaches and international standards on digital forensic science, such as those found in the ISO 27000 series, which I'm sure many of you will be familiar with. There's also been a lot of research into this to show what the available data artifacts are from common IT systems such as Windows or Linux. And because we understand what these artifacts are and we understand their inherent architecture and structure, forensic investigators can make clear predictions and underlying assumptions as to what information this data could potentially yield and why these artifacts are particularly important. In this study, I should note that we define artifact as a piece of data or an object which has some potential evidential value within a forensics investigation. The limitation in ICS, if we move over to that domain, is that currently the data has been referred to in kind of generic forms and just by its memory structure. So we read a lot about volatile data being important, and also, you know, considering non-volatile data and logs. And while this is certainly important as an initial step, it doesn't really tell us a huge amount as to kind of what information that data could potentially yield. And so our research is sitting, if we move into figure 2 on the right-hand side there, it kind of shows a simplified digital forensics process. Our research fits in between this identification and acquisition stage, where we're asking what are the available devices that we can acquire data from. In our case, it's PLCs. And then what are the available artifacts that we can acquire? And we think that it's really important to address this question and have more of a detailed understanding on it before we can really move into developing acquisition capabilities for ICS and for components such as PLCs. Okay, so our research model, or research method, sorry. So we looked at 3 PLCs, and the reason we chose 3 PLCs is because we wanted to not only look at the differences in available artifacts between models within the same vendor. So in this case, we've got an S7-1500 and an S7-300, both from Siemens. But we also wanted to look between different vendors of PLCs. So we have an Allen Bradley Control Logics PLC there as well. And these 3 PLCs were connected up into an Ethernet network to a Windows 7 workstation, which contained the programming software for each of the PLCs. So we had the Siemens TIA portal and the Allen Bradley Studio 5000 software, which is used to write the hardware configurations and the application program and any process variables that are required for the PLC to perform the job that we want it to do. So we did this, we wrote some simple programs and configured and commissioned the PLCs through the hardware configuration. And we allowed the programs on each of the PLCs to run. And the reason we did this is because we wanted the PLC to generate some dynamic data as well as having the static data, so that we wouldn't be just looking at data that we'd put onto the PLC, but also data that the PLC would generate through its normal operational environment. And figure 4 there in the bottom right just shows an example of what one of these application programs would look like in a language called ladder logic, which is commonly used for PLC programming. So how did we acquire the data from these PLCs? Well, we used a communication architecture that's common across many different PLCs. It's often referred to as a request response architecture. And the way this works is you'll have a PLC and it will either receive or it will send data on the network using this architecture. So in this example, we have an HMI, which is a human machine interface, essentially just a glorified touchscreen that operators use to communicate and control with plant floor operations. And that might send a request to a PLC asking for a timer value or an update on a pressure or temperature gauge. The PLC will receive that, and using the function code that's within that request, it will retrieve the data from memory, pass it back to the CPU and to the communications processor, and then send that back into the network to the HMI. The reason we use this functionality is because it's inherent to the PLC. So even though we can't, as of yet, provide any detail on the forensic soundness of this process, we can be reasonably assured that the data that we're receiving is true to what's on the PLC. So to leverage this functionality, we use 3 third-party communications libraries. The reason we used 3 is because the PLCs that we chose all use different communications protocols, just to make it a little bit more confusing and challenging for us. So the S7-300 uses something called the S7 communication protocol, which is an early implementation of Siemens Ethernet-based protocols. The 1500, being a more recent device, uses the S7 Communication Plus, which does allow for some security and some integrity checking on the communication links. And then the Allen Bradley uses something completely different, which is the Ethernet IP protocol. And it's important to note that even though these protocols are different at application and session layer, they all run on Ethernet, and they all are essentially TCP/IP based protocols. But the reason we had to use different libraries was to be able to make use of the different inherent structures of these. And so here's an example of one of them. This is the Siemens S7 communication protocol, which is the S7300 PLC uses. And you can see here, what we do is we issue a function code. In this case, we've said read variable, but we could issue a number of functions, such as to write data. Although obviously from a forensics perspective, we probably wouldn't want to be writing data to potential evidence. Then we define underneath what area of memory we want to access. So in this case, we've accessed data blocks, which could contain dynamic data, but there's a number of different memory areas we could access through different access codes. This is just an example of one of the protocols. Obviously, don't have time to go through all three of them. The paper goes into a bit more detail, but it was just as an example to show the structure of how these work. Okay, so what did we come up with? Well, we from the available artifacts that we acquired, we came up with a forensic taxonomy, and you can see from this that there were a number of artifacts we could acquire, but also we were able to place these artifacts into high level, what we've called forensic data types, and we'll go through each one in a little bit more detail now, rather than just having the one taxonomy on the page and trying to go through it. Okay, so the first data type we referred to was variable content data. And this is very much dynamic data that's updated in real time as the PLC is operating and processing its application program that we'd written beforehand. So the values that we get from this are not the program objects that we initially implemented, but the actual values that these program objects are receiving and sending back to the PLC through the physical operational environment. So for an example, we would get digital input and output values, and these would be the values of the tags that you can see on the screen here in the ladder logic code. We're also able to get some more kind of analog dynamic data. An example here is through timers. We were able to get the elapsed time of specific timers, but there was a whole range of other bits of data that we were able to get, and we need to do a bit more analysis into understanding how the structure of that data is different between different PLCs. Okay, the second data type we refer to is the PLC Application Code. And this is very much the application program that we've written at the start of the work and downloaded to the PLC. So this would normally be written by an operator or a user for a specific reason or a specific function that they would want the PLC to execute in order to meet the requirements of the operational environment. So we were able to acquire the raw application logic, as you can see there, and I'll go through that in a bit more detail in a minute, but we were also able to acquire quite a lot of metadata on the actual code. Interestingly, we could get some checksums, which I should stress are vendor specific, so the strength of these checksums is maybe not the same across the board between different PLCs, but also interestingly, we were able to get quite a lot of timestamp data. So commonly in forensics, we refer to as MAC timestamps. So this is modified, accessed, and created timestamps for a specific piece of data. PLCs operate in a little bit of a different way. There's some different terminology. So trying to kind of sift through that and figure out what terminology is transferable between IT and ICS is really important for forensic investigators. So as I said, also we could access the application code. And we were able to identify a few signatures within that code. So, for example, the start of a piece of ladder logic represented in blue there the actual data that's contained within that segment of code. So in our example here, we have 4 input tags and an output tag, and then the end of a piece of ladder logic to signal, kind of moving on to the next part. We need to do some more work in the future to really understand the different structures between different PLCs and how the signature is different between different models. Okay, so the third data type is PLC metadata, and this is very much data that's particular to the hardware setup and commissioning of the PLC when you first introduce it into the system. So from this, we can get a lot of information about CPU numbers and serial numbers and other modules that might be attached to the PLC, but we can also get firmware information and system date and time. Interestingly, with one of the PLCs, the S7300, we were able to acquire security configuration information, which for anyone that knows PLCs reasonably well, you'll know that they don't inherently often have a lot of security enabled. Some of them do come with some access control, some better than others, certainly more recent ones. But even when they come with that, they don't actually have it enabled as default, and many industries don't really enable this functionality, or they do, and it has default passwords that are in either transferred in plain text or contained within technical documentation. So it's interesting to be able to see that we can acquire data on this, because this could be an area to indicate compromise within a system. Okay, and then last but certainly not least is device diagnostics and logs. So in the ICS world, logs are often dismissed to have really much security or forensic value. Logs were really developed to or designed to help engineers and operators debug plant faults in order to get the system back up and running. And so there's a lot of questions as to whether they really have much forensic or security utility. But we thought that it's not right to just dismiss them entirely. They are a source of information and a source of data. And certainly if we take our knowledge of IT forensics, there could be some meaningful information, certainly as a first port of call for indicator of compromise. To acquire the device diagnostics and logs, we didn't use the functionality that we use for the others, so that the communications protocols, but we got this from the vendor programming software and environment. And you can see that there were a number of different artifacts we could get, to show maybe there were firmware updates on the PLC that shouldn't have been done, or perhaps there was application code maliciously downloaded to the PLC. Now, the log wouldn't indicate that this was malicious. It doesn't have security function codes or indicators, like you would find in Windows systems, but you could possibly use the information to guide you on that investigation. Okay, so just to kind of start to conclude this work, so I included this graph to illustrate the coverage of artifacts that we looked at across different PLCs. The y-axis indicates the 4 different data types we went over. So 1 to 4, it's variable content data, the application code of the PLC, and the metadata, and then device diagnostics and logs. And then the x-axis at the bottom shows the percentage of acquirable artifacts within those data types by each PLC. And so I included this not just to show as face value the obvious of difference between of coverage between different PLCs, but also to highlight that we're at different stages of acquisition capability between different devices. One of the big challenges with forensics in the industrial control system world is that you don't have a leader in the market in ICS, where you would expect Windows to own a large percentage of the market. Even though Siemens does own a large percentage of the market in Europe, it's not the case for the whole world. And so if we develop one capability for one device, it's not necessarily transferable as the specific technical attributes of that are transferable over to another device. And a lot of this is down to the technical documentation available. So, you know, the S7300 PLC was used was the one that was targeted in the Stuxnet attack, which I'm sure a lot of you are familiar with. And so there's a lot of technical documentation about it because there's been a lot of research on it. Whereas the 1500, because it's a more recent device, Siemens have kind of kept their cards close to their chest, so we don't know as much about the inherent memory structures of this PLC. So it makes it difficult for us to acquire artifacts from all PLCs in the same way. Okay, so just to conclude, I'll just leave you with 3 points, or 4, I guess, if you include the future work. PLCs are rich in data that could be of evidential value. So as we see, there's a number of detailed data artifacts that we can acquire from PLCs that could provide evidential value in a forensics investigation. Although it's really important to note that more work needs to be done to understand the potential significance of these artifacts, particularly if we want to establish guidance of the prioritization. Obviously, in industrial control systems, we have this additional risk of safety that we don't have, and system availability that we don't necessarily have in IT to the same degree. And so it's important for us to establish how we prioritize the acquisition of artifacts from particular devices, because we don't want to introduce any system downtime into safety critical systems. Secondly, not all data artifacts can be acquired from all PLCs. So the previous slide kind of highlighted this, but I'll just reiterate that it's important to know that there are still questions over the forensic validity over the acquisition capability that we do. So the methods that we followed, that we used for this, don't necessarily follow forensic guidelines in terms of data being admissible in court. So it's really important for us in the future to think about that question as to what really are our objectives of forensics in ICS. Is it for attribution, or is it just to show that we've had a breach and we need to patch our systems, which is a whole different challenge in itself. So I won't go into that. And then thirdly, there's a need to better understand the relationship between data types and the artifacts. It's not enough for us to just provide names of data artifacts, but we need to understand the structure of these artifacts and the relationship between data types, between different models of PLC. And this is part of future work that I've included in this slide. So we're looking to see if we can formalize the taxonomy into more of an object-orientated model to show the differences between different PLC models and what artifacts are common across all PLCs and what are more unique. And that concludes my presentation. I'd be happy to take any questions that you've got.
Thank you very much, Marco. It was great. We have a few questions for you. The first one is, do most PLCs have tools to ease reading the binaries and associating them with the commands like disassembler will do?
So PLC vendors provide an ability for us to acquire the application code from the PLC. And although that's really useful, there's a lot of work to show that actually the vendor software has a large number of vulnerabilities that can be targeted to prevent the integrity of that data. So from a forensic standpoint, you wouldn't be able to rely on the vendor software itself to acquire that data alone. Currently, as far as I'm aware, there's no publicly available PLC forensic acquisition tools. I know that it's an area that a lot of researchers have been focusing on and trying to drive towards, what is it that we want to acquire and how do we acquire it? But because of the technical discrepancies between a lot of PLCs, it's really challenging to develop a kind of golden bullet solution almost that will fit around many different devices.
So can you give us some examples, like let's say in the Stuxnet case, which ones of the data artifacts that you were mentioning would you detect that they've been changed or they've been corrupted?
Yeah, so it's a really good question. So Symantec did a really good report on Stuxnet actually back in 2011. So I'd recommend people to go and read it if they're more interested in the area. But it kind of linking it to our taxonomy, they changed some underlying process variables to do with timers and counters and motor speeds and things like that. So being able to acquire the dynamic data of the PLC would be really important for us to be able to have an indication. But that probably wouldn't be enough, and we would need to be able to acquire the application code as well. One thing Stuxnet did is it intercepted the communication between the engineers and the PLC. So when the engineer performed an acquisition through the vendor programming software, they saw what they thought was legitimate programming software from the PLC. Actually, what Stuxnet was doing was it was intercepting that communication link, and we weren't able to see what was actually on the PLC, which was malicious.
So from the security point of view, more than worrying about the security of the PLCs, because they are usually, let's say they usually work correctly unless they've been modified somehow. What it worries me more is that you were using a Windows 7 machine.
Yes, yeah, I know. I kind of thought about whether I should include whether I say Windows 7 or not and just say workstation. But the reason we use Windows 7 was because the programming environments for these systems until recently have only ever worked on Windows-based systems. So recently there is a move for some of them to move to Linux. I'm not aware of any moving to Apple to Mac OS yet, but so that's one of the reasons we used it. And also the reason is that the communications libraries were easier to execute, funnily enough, believe it or not, on a Windows system than Linux. So yeah, it's a very good point. I think any ICS that's running Windows in the background, particularly when you find systems running Windows XP, is deeply worrying. So
hopefully it's something that is going to change in the future.
Hopefully,
but yeah. Thank you very much, Marco. Again,
no problem.
We don't have any more questions for you.
Okay.
And we hope that you can all join in the keynote speech, which would be 3 p.m. UK time. So thank you again to the panelists, and see you later.